it is more expensive comparing to the crown ether complexes, and it is very difficult to prepare, but it is highly selective, and its strength of binding is very good, or we can say that it is a moderate strength of binding. You can see here the synthesis process of kryptonites is very difficult. Most of the time, it will synthesize at least 3-step, 2-step organic reactions by using 3, 4, just like that. So the synthesis of kryptonite, it is not very easy. It is generally more expensive also, and it is the synthesis method is also a little bit lengthy or difficult. But when you prepare a kryptonite, it has more rigidity. The kryptonite macrocyclic rings, it has more rigidity comparing to crown ether, and the crown ether complexes are little bit flexible in nature. Okay, so when the rigidity is more, the macrocyclic rings rigidity, it will increases. It will create a proper cavity size. So some few particular guest molecules or some few particular cations, they can fit inside it. But when the particular appropriate cation, it will fit inside the kryptonites, the stability, it will be bigger. It will be much more comparing with the crown ether complexes. Or some of the reactions, it can also use this as a catalyst. Okay, and it can also used in synthesis of the alkalides or electrodes, just like that. Okay, so you need to remember at least 2 to 3 uses of kryptonites. So they can ask what are the defined kryptonite compounds and its binding tendencies with few some examples, its structure, and and they may ask the questions just like at the end. Write down 2 or 3 uses of kryptonites. You can add it. Then further, we will discuss about the cyclodextrins. So particularly cyclodextrins, these are the oligosaccharides or polysaccharide compounds. They can make interlink in between them by using alpha glycosidic bonds, or we can say this linkage is just like 1,4 linkage. Okay. So here you can see here, this is the structure of cyclodextrins. Here this bond. So one ring connection with another. This one you can told it just like a 1,4 linkage. So some for one group, it may be this carbon center may be named as 1, but for this ring, this carbon center it is named as 4. Just like here, this one will be 1, then it will be 2, 3, 4. Here it will be 1, then 2, 3, 4, just like that. So it is called 1,4 linkage. So one side of the one glucose, it can connect to 4 carbon center of the another glucose. This is called 1,4 glycosidic bond. Okay. So cyclodextrins are composed of 5 or more alpha diglycopyranosides units, and its linkage it will be always just like 1 to 4 linkage. Okay. So it is basically 3 types: alpha cyclodextrin, beta cyclodextrin, and gamma cyclodextrins. Or in alpha, the number of glucose or subunits we can say 6, in beta it is 7, and in gamma it is 4. So particularly the cyclodextrins, basically they contain a number of glucose monomers ranging from 6 to unit in a ring or creating a cone shape structure. In previous class I already show you they can also form, they are just forming cone type structure. So here the circle is just seems like it is a circular. No doubt it is circular, this throughout this plane, but along with this circular path, they will form a cone type structure like that. So here, this is alpha cyclodextrin. We can count here how many rings are present: 1, 2, 3, 4, 5, 6. So these are the 6 glucose components. They are interlinked with each other by alpha 1,4 linkage. Yes or no? And this is beta cyclodextrin. Here you can count, or you can also count the monomer units. Here you can count, or you can just see 1, 2, 3, 4, 5, 6, 7. 7 glucose units, they are interconnected with each other. And in gamma also, 8 glucose units, they are interconnected to each other to form a macrocyclic ring like that. So from alpha to gamma, Here we can say the monomer units also increases. Along with increase in monomer units, the cavity size also increases. That means I can say the cavity diameter, it will here it will be less, and here it will be cavity diameter, it will be more. That means it can absorb or trap a larger gas molecule. It can absorb or trap a smaller gas molecules. So particularly throughout the plane, they will form just like a cone structure like that. And the cone end or the surface of the cone, there will be OH molecules also available, and the below surface of the cone also OH molecules are available. So one of the OH is called primary alcohol hydroxyl groups, and another OH groups are called secondary OH groups or hydroxyl groups. So these two types of OH groups, they have very much importance in organic synthesis reactions because this OH participates with the substrate or reactant to perform a reactions, and this OH also sometimes they also participates. So these two OHs, primary hydroxyl groups and secondary hydroxyl groups, they have important role in participation in organic reactions or synthesis methods. The same thing, cyclodextrins are constituted by 6 to 8 glycopyroxide units. These subunits are linked through 1,4 glycoside bonds, same thing. And the cyclodextrins have inverted pod shape structure. This is also called sometimes pod shape structure, with the larger and the smaller opening of the inverted pot exposing the solvent secondary and primary hydroxyl groups. So one will be secondary primary hydroxyl group and another will be primary hydroxyl groups. Because of this arrangement, the interior is not hydrophobic, considerably less hydrophilic, and the aqueous environment thus able to host other hydrophobic molecules. So here one can say the outer part. In outer part, particularly the OH groups are present. So the outer part is no doubt this is a hydrophilic. These groups are hydrophilic, but the interior, someone can say if outer will be hydrophilic, interior will be hydrophobic, but it's not hydrophobic. But it is, I can say this is little bit or less hydrophilic nature, and the outer side groups this is more hydrophilic. Okay, so the inner part it is less hydrophilic, but the outer part it is more hydrophilic. So if the outer part will be more hydrophilic, it can interact the polar solvents. Yes or no? It can interact the polar solvents. If the interaction of a hydrophilic substrate with a polar substrate occurs, then definitely cyclodextrins are soluble in this polar solvent. So that's why, and the cyclodextrin containing any types of guest molecule, and a it is diluted with any solvent, particularly polar solvent. If it is water or alcohol, then definitely cyclodextrin supramolecular chemist compounds, these are soluble in water or polar solvents due to its outer part, due to the hydrophilic nature of the outer part of the cyclodextrin. So here you can see in constant, the exterior part is sufficiently hydrophilic. That means exterior part is more hydrophilic to impact cyclodextrin, water soluble. Due to the hydrophilic nature of the outer OH groups, they can make interaction with the polar solvents, and that's why these are the water soluble compounds. Okay, particularly these are not suitable for typically organic solvents. So organic solvents means we can take a benzene, toluene, which are non-polar in nature. And here the cyclodextrin containing guest, this is containing hydrophilics groups in the exterior part. That means it is polar in nature. So particularly, like dissolves like fluid. So polar solutes, these are dissolved in polar solvents, and non-polar solutes, these are dissolve. They can dissolve in non-polar solvents. So its outer part is hydrophilic. That's why its behavior is just like hydropolar nature. So it needs a polar solvent to soluble. But these are not soluble in typically the organic solvent, particularly the non-polar type of solvent. THF, you can take benzene, like that. You can take toluene. It will be non-soluble in these organic solvents. Screen visible also ସମସ୍ତଙ୍କୁ?
Yes, sir. It's a visible.
Okay. So the same thing it is written. And the another benefit of cyclodextrins are these are inexpensive and these are water soluble natural products. It is generally non-toxic in nature. Okay, and it is available in commercially available, and these are used mostly artificial enzymes. So you can create a enzyme by using cyclodextrin, and you can add a guest molecule. The guest molecule is particularly called as just like substrate, just in lock and key theory. That means these cyclodextrins they will behave just like a lock, and the guest molecule they will behave just like a key. Okay, so they can provide cyclodextrins can provide good enzyme sites, and the chiral separators and chemical sensors and in drug industry also they can use it. They can use cyclodextrins. So due to its remarkable inclusion capabilities with some organic molecules, okay, so most of the reactions they can be catalyzed by using the cyclodextrins. So basically, cyclodextrins are used in organic synthesis reactions. When particularly the oxidation reactions, mostly cyclodextrins are used. And sometimes also cyclodextrins and their derivatives they can also use as a phase transfer catalyst in synthesis of the organic compounds also. So you can check here so many organic reactions. Here we are using a aldehyde, and we are using the beta cyclodextrin and water solvent and NaClO3, the oxidizing agent, and here the aldehyde CHO will get converted to a terminal aldehyde. That means here the breaking of the bond occurs, and that this will be the side product. One, two, three. So the beta cyclodextrin they can be used in the formation of cinnamaldehyde. This is called cinnamaldehyde formation by kone pariba beta cyclodextrin to am kone kariba we can use it. You can see here the exact reaction. You are taking a alcohol, and along with you are taking beta cyclodextrin. Okay, and it is forming aldehyde. We can see here. This is the cyclodextrin. This is the alcohol, and the cyclodextrin it is just formed just like a protective layer around this aromatic ring, and this alcohol group it will interact with the secondary OH groups of the cyclodextrin. Here you can see. So after interaction with this carbon center of the alcohol, they will form a just like a transition state like that. And in the next step, they will remove the OH minus group from this structure. That means if you will form a carbon and OH, then definitely carbon center it will get positive charge, and this oxygen center in alcohol they will get the negative charge. Okay. So if you move the electron density in between CH towards this OH group, then definitely this bond will break. If this bond will break, the OH minus it will separate from the structure, and they will form a intermediate structure like that. And in next case, ClO minus it will act as a good nucleophile. It will attack to the carbon or electrophilic center. Then it will form a structure like that. And again the negative charge on the oxygen that will shift it towards this carbon center, and this will form here a double bond. So along with the shifting of negative electron density from oxygen, the oxygen and chlorine bond it will break, and this oxygen chlorine electron density it will shift it towards the chlorine. That means in the next step the chlorine Cl minus ion it will be removed from the structure, and it will form a aldehyde like that. And in further step, the OH minus ions it will stabilize the secondary alcohols, and this main aromatic ring it will get only connected with the aldehyde group, and the structure will be like that. So here the nucleophilic or any another group they cannot participate in with the ring, or they cannot interact with the ring. So sometimes cyclodextrin they will form a just like a protective layer around the aromatic ring, and only the alcohol group or CH2OH group it will make interact with the OH. Okay, so initially it will in the form of OH also, and finally after the removal of the structure, again it will in the available in the same type of structure. So sometimes they can act as a good catalyst also. Catalyst means initial structure and final structure is same, but it will participate in reaction. It makes the reaction faster also. Okay, so basically when you are using these supramolecular compounds, the basic benefit is that we are getting the yield in much more amount. Generally, in organic synthesis, there will be selective of organic oxidizing agents or reducing agents or any types of agent for formation of a particular compound. But by using supramolecular chemistry, we are getting the products in a good yield. So here, the yield amount you can see here, it is more than 99%. This is a very good yield amount. Okay, so this is one of the benefit of the alpha beta cyclodextrins that can participate in a oxidation reaction to form a good yield product. So you can see here, these are the mild oxidizing agents, NaClO and HCl, and the benzaldehyde could oxidize to benzic acid. So if you are using, if you can use also more strong oxidizing agent, then this further this aldehyde they can also get converted to carboxylic acid, or here this benzaldehyde they can also get converted to benzoic acid. So under the optimized condition, the yield is up to 98%. So in these reactions, the reactants are inexpensive, and beta cyclodextrin it is also inexpensive and it can be recycled. That's why it is treated as a catalyst. The mechanism was that the oxidizing agents oxidize the benzaldehyde to carboxylic acid when the acid provides the proton, particularly here after the formation of COH or carboxylic acid. Here you can see after the formation of aldehyde. Here, if you are taking the acidic group HCl, then the H plus it will interact with the oxygen atom and it will form a structure like that. That means here the pi electron density it will be shifted towards the oxygen. The oxygen will be more electronegative, and this O minus it will interact with the H plus and it will form a OH ion. And here in carbon center, just like in previous case, in this case the positive charge it will be written on the carbon center. That means you can break one bond here and you can shift the electron density toward oxygen atom. The oxygen will be O minus and the carbon will be C plus. And again this O minus it will interact with the H plus ion. It can be, and this final structure will be like that. So further ClO minus it can participate in this reaction or with this carbon center, then it can again convert it to C double bond OOH like that. Just like in previous case, ClO minus will participate with the carbon center. Again, it is forming a C double bond O. It is forming a carbonyl group. So here also in this center, it can just form a carbonyl center, and the OH group is already present in this structure, and it will be treated as carboxylic acid group. So we can, by using beta cyclodextrin, we can convert alcohol into aldehyde, and if you take strong oxidizing agent, you also convert the alcohol into carboxylic acid also. So sometimes we can also we can get converted to thiol to olefin also by using beta cyclodextrin. Here is one reaction you can see here. This is the thiol group, sulfur group. Okay, we're using beta cyclodextrin. So out of all these reactions, you need to remember some of the, particularly some of the oxidation reaction like that, and you need to remember these types of reduction reactions also. You can see here we are using sodium borohydride. So hydride adding agent, this is a good reducing agent. Yes or no? So if you are adding this cyclic ring inside the cyclodextrin, they will form a structure like that. That means this OH of the cyclodextrin will initially make an interaction with this carbonyl center. Then further, if you are adding NaBH4, this is a reducing agent, or this produces H minus ion or hydride ion. And this hydride, it will get added here in O center. And this carbonyl group, it will be get converted to like that. So LiAl, lithium aluminum hydride, or NaBH4 or CgMBH4, these all are hydride agent that can create hydride anion or H minus ion. Okay. So the NaBH4, it will be in the form of Na plus and BH4 minus. And from this BH4 minus, one of the H minus, it will be get separated from this BH4 minus. And this H minus, it will attack to the particularly the carbon center. And this, it will get converted to O minus, and further addition of H plus ion occurs, it will get converted to the alcohol also. So beta cyclodextrin, or particularly cyclodextrin, it is very useful. That means it can used as a catalyst in oxidation reaction also, and it can also used as a catalyst in reduction reaction also. And some bridging complexes, or it can also used as a catalyst. Okay, so these are all the uses of beta cyclodextrin. Okay, and the beauty of beta cyclodextrin is it is inexpensive, and it is water soluble, and is non-toxic. Okay, so it is easily available in commercially. It is also easily available. Okay, so it has many applications. So that's why cyclodextrins are much more popular than the kryptanoids or chromethers. Okay, then we'll discuss about cyclophanes. Particularly, cyclophanes are these types of rings. That means these types of rings particularly contain the aromatic rings also, and some aliphatic chains also. Okay, so you can see here these types of structure. This is the aromatic ring, and these are the aliphatic chains. This is the aromatic ring, and these are the aliphatic chains. That means it contains both aliphatic groups, and it contains both also the aromatic groups. You can make a reading which contain aromatic rings as well as aliphatic units. So the particularly the aromatic group, it provides the rigidity to the structure, and the aliphatic group, or we can simply say any non-cyclic group or any linear chain, they are little bit flexible in nature. But when you are making any bridging complex or any cyclic complex, the rigidity of the structure, it will be more. The structure will be little bit more planar. Okay, so here two types of groups are present, but out of them, particularly the aromatic group, it contributes the rigidity of the structure. That means it is responsible for the rigidity of the structure in cyclophanes. And the aliphatic group, it will be little bit flexible in nature. So cyclophanes plays an important role in host-ghost chemistry, particularly host-guest chemistry. Okay, that means phanes means containing molecules, so interaction with pi systems. So in this structure, sometimes this aromatic ring pi system, it will make interact with the guest molecules. So here the guest molecule, it can be a cation, or it can be an anion, or sometimes it can be a neutral molecules also. No issue. So particularly we can say cyclophanes, it can contain one aromatic ring also, or sometimes it can contain also more than one aromatic units. And these are the naming of this cyclophanes. You can see if this is one position, if this is four position, this is named as para cyclophanes. And here you can see here this is one position, this is two, three. So this position is just like meta position. If it will be the substituted group side, and it will be one, two, three. This is just like meta position. So this is named as meta cyclophanes. And here this is n dash cyclophanes. We can name simply it is just like that. That means on both sides, n dash, that means on both sides the number of cyclic chains are present. Here n means only on one side aliphatic chain is present. These are some other examples you can check here. Orthocyclophanes, metacyclophanes, and these are called paracyclophenes. And this is called 2,2 paracyclophenes, this type of structure. And this is called 2,2 meta. Here you can see this is 1,3 position, so you can told it just like meta. And this is called orthocyclophene. And these are some other derivative structures. And here some interaction is just like para. You can see this is 1,4 position, and here this interaction of this aliphatic chains, they're making 1,3 position linkage. That's why sometimes we can call it just like meta paracyclophenes. Here you can also check this one, this ring, it is interconnected to the aromatic group through 1,4 position, 1, 2, 3, 4. So we can name it just like para group. Here also, this cyclic ring, they are interlinked to the aromatic group 1, 2, 3, 4. We can name it just like as also para. So here we can say NN para cyclophenes. So you need to check the particularly cyclic rings connecting unit. Here it is, if it is joining to this position, we can name it just like one. Then this ring connected to another position here. So here it will be one, then it will be two, three, four. So just like this interaction is called para connectivity. But here this ring is forming one, two, three. So here the connectivity we can name it just like as a meta group. So this is called meta para cyclophane. But here both are para. So you can named it just like that, para cyclophane. Okay, so particularly the paracyclophanes, they can adopt the board conformation, which is normally very unstable in cyclohexane rings. But but here they can still maintain in aromaticity in the board conformation. But generally, benzene in board conformation, it will be very highly unstable form. But paracyclophanes, they can make board conformation also, and this time they can also retain its aromaticity also. So when the value of n or the aliphatic rings change size, this n value, this n values, when the value of n is smaller, larger the deviation for the aromatic planarity. So that is not initially when the n value will be lower, the planarity is less. But if gradually with increase in n value, the rigidity of the structure increases, and throughout the structure, the aromatic ring is also in planar form. But these cyclic rings, with increase in the n value, they again get more rigidity inside the structure. So if the n value will be small, that means it will be more flexible, it will be little bit deviate from the planarity. So in 6 you can see paracyclophanes, which is one of the smallest and stable cyclophanes. And the X-ray crystallography shows that the aromatic bridgehead carbon atoms makes an angle 22.5 with the plane. Okay, so it's fine. So when it is in board conformation, you can see it's making an angle with the molecular plane at a 22.5 degrees Celsius. Okay. So this structure is also important, but you need to remember this one. This one is the proper representation of cyclophane structure. This is aromatic ring, and this linear chains or linear groups will be arranged just like. And this is the synthesis method of the cyclophanes. You can see here we are initially for the formation of cyclophanes. Initially, we need to take the spiro compounds like that. Okay, so this name reaction that's forming from 1 to 4 by Bumford-Steven reaction. This is called Bumford-Steven reactions. So pyrolysis, this C carbonyl O bond at this carbon center, they will get converted to a carbene structure. And further, this carbene, if you heat this carbene at 250 to 400 degrees Celsius, they will get converted to the cyclophane structure like that. So by using Mumford-Steven reactions, You can get converted a carbonyl group into a carbene intermediate, and further if you heat the carbene intermediate, they will get converted to the cyclophane structure like that. Okay, so this is another synthesis method. If you take this reactant also, and if you are adding this oxidizing agent also at 0 degrees Celsius, they can also get converted. So there are two methods. In this way also you can synthesize the cyclophane, or in this way also you can synthesize the cyclophane. So if you he- treat this substrate with this oxidizing agent, they will initially get converted to this structure. If you heat further at 50 to 90 degrees Celsius, they will get converted to the cyclophane structure. So this is the synthesis method of the cyclophanes. And other types of cyclophanes also. Okay, here we can see also other types of cyclophanes that are involving uh, not only with the carbon atoms. That means here the aliphatic groups that are not involving only the carbon atoms, that are also involving carbon along with oxygen atoms, and sometimes these are involving the sulfur groups. This naming, the naming will be this type of structure you can call it cyclophane type oxathia crown ether. That means it is a cyclophane compound, along with it looks like a little bit crown ether complex. Crown ether complex means here the oxygen atoms are present, and this is a cyclic group. This looks like a crown ether, but along with oxygen also sulfur atom is present. That's why this is so this is also named as thia. So thia, the word thia, it comes from this due to its this sulfur group. So this is a other or special type of cyclophane, and you can also synthesize it by taking the 1,4-phenol group. Here also you can take these two substrates. You can add a base just like that. Get to CO3. They will form initially a cyclic group, and further you can add cesium carbonate with a DMFO and another substrate. If you add another substrate, they can also interact with this bromine atom, and this is bromine atoms. These are the good living groups. You can eliminate it. They can form a cyclic structure like that. So these are another important supramolecular host molecule complex. This is called cyclophane. And further, we'll discuss about another important host molecule. This is called calixarin. Calixarin, it is synthesized or reported first in 1872. So these are the cyclic oligomers. It can form by the condensation of large number of phenols or functionalized phenols or substituted aldehydes. A calixarin is a curved-shaped molecule. Just it seems just like similar, just like a cyclodextrin. But in cyclodextrin, the upper part and lower part it is covered by hydroxyl groups. But here, the upper part is covered by the alkyl groups, and the lower part it is covered by the OH groups. That is the difference. That means in calixarin synthesis method, the initial substrate is a phenol group, and this phenol along with this phenol group, the OH group in the ring, there will be substituted groups, or the substituted group is R. So basically the R will most of the time this is just like a taut butyl group, or this is a bulky group that gives rigidity to the overall ring. So initial substrate, if you are taking an initial substrate or initial alcohol group for synthesis of calixarin, the alcohol group will be like that, and R most of the time it will be a taut butyl group. Okay, so this is the structure of one of the calixarin, this cup-shaped structure. One of the side of the cup, it is surrounded by R group. That means this part will provide a hydrophobic environment due to the presence of the alkyl groups. And the lower part, it is covered with the OH groups. That means it provides a hydrophilic environment. So these types of host molecule, they can provide both hydrophilic environment also, and they can provide also hydrophobic environment. So you can synthesize different types of calixarin by using different types of substituted alcohol groups. So we are taking the para alkyl phenol groups, they will form the structure like that. Okay, so this is also another types of Calix-Zaren group. So you can see also Calix-Zarenes have generally hydrophobic cavities that can hold smaller molecules or ions and belong to the class of cavitands known as host-guest molecules. That means the cavity or the environment is hydrophobic. That means the inside environment of the cup is hydrophobic. But in cyclodextrin, the inside environment is not hydrophobic, but it is less. It is little bit hydrophilic in nature. But here you can say that the inside environment of the host molecule is hydrophobic. So Calixarin 4 RN has 4 units, but Calixarin 6 RN has 6 units. So you can just remember these are the monomer or subunits. So if the naming will be just like that, that means it can contain these types of 4 groups connected with each other to form a ring. And if the naming will be this, the Calix 6 RN, that means it contains 6 units. And the corpse structure it will looks like that. Actually exactly it will looks like that. So it is three part. One will be the upper ring, another will be the annulus, or another will be lower ring. Okay, the OH, the lower ring contains some most of the time OH group, and sometimes also contains the OR group, substrate group, methoxy group, or ethoxy group, like that. But the upper part it always contain the alkyl groups that will create a hydrophobic environment. And the middle part of the cup it is always surrounded by the aromatic rings covered with pi electrons. Okay, you can see the structure like that also. You can draw the structure like that also. Okay, but this much is sufficient for you for your master degree course. So these are the different group types of host molecules we will discuss. Okay, and if there will be some other groups, you can study in your study material. But these are the basics groups which are most important. From these types of groups, they can ask several times the question. Okay. Then again, further we'll discuss on some few types of interaction in the supramolecular chemistry. Now we'll discuss about what are the kinetic and thermodynamic stability created when the binding process occurs in between the host and the guest molecules, or what are the effects that will arises when a guest and host molecule it will interact with each other. Okay, so basically now we'll discuss about the cooperative effects, what is anti-cooperative effects, what is allosteric effects. That means if a guest molecule is bind with, initially it will make an interaction with the host molecule. Then after that, what will be the condition? If the condition can be like that, it can support further addition of the guest molecule, and the condition it may be like that, it cannot support further addition of the guest molecules. If it will support the further addition of the guest molecules, it will be treated as just like a cooperative effect. If doesn't support, we can treat told it just like it is a anti-cooperative effect. Okay. Then after the interaction, whether the binding process or the interaction this is thermodynamically stable or whether it is kinetically stable, we need to observe all these properties here. Okay, so one by one we'll discuss. First thing is that if you add three guest molecules with a host molecule, you are adding three guest molecules with a host molecules and the interaction is good, then if you calculate every guest host interaction or every guest host stability, then you can suppose you are adding one guest molecule and with the host, and the host has three active sites to interact with the three guests. So you are adding one guest here, you are adding another guest here, you are adding another guest here. Okay, so if the guest host interaction here, if this guest and host interaction, it will create a stabilization energy of 5 kilojoule. This guest host interaction also creates a stabilization energy of 5 kilojoule, and this gas interaction it will create a stabilization energy of 5 kilojoule. So we can say the three complex overall creates a 15 stabilization energy. But actually, when at a time three guest molecules it will interact with the host molecule, it will not create this just like sum of three individual interaction energy. It will create larger than that also. That means experimentally, if you calculate the overall guest host interaction, it will be more than 15 kilojoule. It will be just like 20, 25, like that. So this concept it is told here. This concept is called cooperative effect. This is called cooperative effect. And the cooperative effect is mentioned here. It is known that the whole is greater than the sum of its parts. In other words, a team pulling together has a greater effect than the sum of many individual efforts. This is called cooperative effects. This concept can be easily applied to supramolecular chemistry. You can read out here. These two sentences are very much important. The whole is greater than the sum of its parts. In other words, a team pulling together is a greater effect than the sum of many individual efforts. So this concept can be easily applied to supramolecular chemistry here also, and these types of interaction is called cooperative effect. So basically, we'll discuss here cooperative effect, anti-cooperative effect, and allosteric effects. Okay. And along with, if a guest and host, this will interact, what will be its selectivity, what will be its complementarity, and other things. So first, we can see here the cooperative effects. So in supramolecular and coordination chemistry, cooperative refers to the phenomena where multiple binding sites within a host species work together. That means the host itself it contains more than one active sites or binding sites that can interact with the guest molecule, that leading to a form a more stable complex than the sum of their independent effects. I already told you when a guest molecule, host molecule, it will provide three active sites and three guest molecules that are interacting with this host. Then if you calculate the stability of the overall complex, it will be more than the individual stability or individual host-ghost interactions. So basically, these types of interaction or these types of effects are arises when a chillet type of effect creates. So chillet effects means when the ligands that will interact with the host, they can form a more cyclic ring structure. When they will form a more cyclic ring structure, the complex will be gain little bit planarity. When it will get little bit planarity, particularly the stability of the complex, it will increases. So in graduation, you know about Chillet effect. If you are using the monodental ligands that cannot create Chillet ligands or Chillet effect, just like nickel NH36. But if you are using En3 means ethylene di, I mean this group NH2, CH2, CH2, NH2. That means the two nitrogen atoms here, the two nitrogen sides that will make an interaction with the metal center or that will make an interaction with the nickel center. And now the environment is it is forming a cyclic environment. If a cyclic environment will create, then definitely this is called chelation. This process is called chelation, and these ligands they will act just like a chilled ligands. So it's mentioning here nickel NH362 minus. That means here 6 ammonia it provides 6 ligands or 6 donor site, and in nickel En3 ethylene diamine also it provides 6 donor site because En is a bidental ligand and each ligand provides 2 donor site to the nickel atom. So he's mentioning that despite the similar Mn bonding, that means in nickel and NH3 also, nickel it will make a coordination bond with the nitrogen, and in nickel En3 also, nickel is making a coordination bond with the nitrogen donor atom. So what is the difference? Difference is that here it is not forming a cyclic environment because these are the monodental ligands. But in nickel En3 it is forming a cyclic environment. So the cyclic environment or cyclic ring is formed due to the chilletry or due to this chillation process. So when there will be formation of this type of cyclic ring, the stability of the complex will be more. So you can see here the experimental data For this complex, this is minus 49.2 kilojoule mole inverse, and for this nickel En3 2 complex, this will be minus 104.4 kilojoule mole inverse. Definitely, if the del G value will be more negative, the reaction will be more feasible and the stability will be. Then we can analyze. So this gain or the chelation process, the instability created by the enchelation process is due to what type of effects? Either thermodynamics effects will affect the stability or kinetic effects will affect this stability. So what it may be, but basically this del G value is particularly due to the two parameters. It will del G value will affected due to two parameters, del S0, del S0, and here the enthalpy and this change in entropy, it will affect to the it will affect to the Gibbs free energy. So in particular the upper complex nickel NH3 complex here we can see, so replacing the 6 NH3 ligands with the 3 EN ligands increases the number of free molecules in solution. That means he's saying that suppose in nickel En3 complex, this is nickel En3 complex, and you are adding 6 ammonia ligands, or you can write just like that. This is a nickel NH3 6 cross reactant along with how many EN groups? 3 EN groups. So in the initial reaction, you can see here, you are adding a single complex ion along with 3 EN, ethylene diamine group. That means initially the number of reactant is 4. But after the addition of this ethylene diamine group to the substrate, it will form a complex like that. Nickel, En3, C plus. And along with how many ammonia ions? 6 NH3. So he's mentioning the same thing. Replacing 6 NH3 ligands with 3 EN ligands increases the number of free molecules in solution. So you can see, if you take the initial substrate, if you add 3 ethylene diene groups, you can see here initially the number of reactants will be, this is 1 and this is 3. It will be 4. So after the reaction performance, or after the substitution of these 6 ammonia ligands to outside and these 3 ethylene diamine groups, it will be form the complex with nickel. Now you can calculate the number of molecules. This is 1 and this is 6. Now the number of molecules is 7. So the number of molecules, it will increases from 4 to 7. If the number of molecules will increases, we can say the entropy will increases, or a del S value will be more positive. So if the del S value will be more positive, this part minus T del S, this will be more negative. If this value will be more negative, mathematically, you think if this value will be more negative, then definitely del G value will be negative. So here the del G will be negative due to this change in entropy. So particularly when an chelating ligands, it will attach to the complex, it will increases the number of molecules. So this increase in number of molecules, it will increases the entropy inside the complex. So the increase in entropy, it will gives rise to change in Gibbs free energy. And here the Gibbs free energy, it will be more negative. When the del G value will be more negative, the reaction will be more feasible. So in Gillette ligand, in presence of Gillette ligand, there will be extra entropy contribution that makes the complex more stable. Okay. So another parameter is that kinetic stability. So when the chelating ligands bind through the multiple donor atoms, so we can easily remove them also. Simultaneously, we can make the bond breaking also, and we can simultaneously make a formation of another complex also. So these rings, it will overall form the stable complex. For this chilled bonds with the metal, it can also sometimes break, and it can easily substitute by other ligands also. So when the product formation will be faster, that will, it can take a lower time, but it is forming the product in a faster way. Then this is called kinetic stability. That means kinetic stability only deals with the faster production. So out of the all the products, which products we are getting initially or fastly? This is called kinetic stability. But if I say thermodynamic stability, it may take more time, but this thermodynamic stability of the complex, it will be more. So here we can see here there is a picture of non-chilled ligand complex, and this is a picture of chilled ligand complex. That means these are the bidental ligands, just like ethylene diamine. Okay, so here the triangles, these are the ammonia ligands. One, 2, 3, 4, 5, 6. And these two triangles here, this is ethylene diamine group, and these types of rod. This represents CH2, CH2 group in between them, just like CH2, CH2 groups. Okay, so when there will be bidental ligand, just like EN, ethylene diamine, it can form a ring like that. Okay, so when there will be formation of cyclic ring, and definitely there will be the stability of the complex, it will be more. So here also it is mentioning initially these types of complex, you are adding three ethylene diamine group, and it will form finally a complex like that. And another example you can take as a chelating ligand is EDTA. You know, popularly in your plus two science, EDTA, ethylene diamine tetraacetate. Or here, if you add four H plus groups on the acetate group, then you can treat, simply told it just like ethylene diamine tetraacetic acid. So H for EDTA means you can just memorize like that. This four O minus groups. Here, this is the structure of ethylene diamine tetraacetate. This one. This is metal complex, and this is the structure of EDTA. If you add four H plus groups, it will attach to this center, this center, this center, this center, and you can name it just like H for EDTA. And it is four donor. It is how many donor atoms? It is six donor atoms. You can see here. This is O minus group. This is the oxygen donor. This is the oxygen donor. This is the oxygen donor. This is the oxygen donor, and these two are the nitrogen donors. So EDTA, it is always has a six donor atoms, and out of these six donor atoms, two are nitrogen donor atoms, and four are two are nitrogen donor atoms, and four are the oxygen donor atoms. And with EDTA, and particularly the hard metals, they will form calcium, magnesium 2 plus, calcium 2 plus. They will form a octahedral complex like that. So in place of M, you can take calcium also and magnesium also. It can form the structure like that. This is called ethylene diamine tetraacetic acid. Or if you only use these O minus groups, you can call it just like tetraacetate group. So basically, when a cyclic ring is formed, basically initially these small rings they will make a strain ring. You can just consider just like cyclopropane, cyclobutane. So when there will be three-member ring and four-member ring, definitely they are forming the ring. But still, there will be more strain inside the ring. But when it moves towards the five-member ring and six-member ring, the strain will decreases and the stability will be increases. So for particularly, we can say for particularly the guest molecule, if the guest molecule is K plus, the five-member rings are optimum for the larger rings to trap them, and if you consider the six-member rings, and then the six-member rings also it has a less strain, but it is little bit more flexible. That means we can say the five-member rings provide the optimal stability. So when you move from 5 to 6, and definitely The strain is also less, but it is again more flexible nature. So the five member rings particularly, they can trap the larger cations. And the six member rings, they are particularly, they can favorable for the smaller cations like lithium ion, just like that. So the larger rings are more flexible, so reduce this the ring strength. But they allow too much conformation flexibility. So they are entropically less favorable and less stable and have a little bit weaker chillet effect. That doesn't mean if you increases the number of the ring size from 6 member, 7 member, 8 member, the stability will gradually increases. So the stability will be optimum value. The stability it makes a better value only for the 5 member and 6 member ring. So here also we can say this is a Podan structure. Podan structure. This is a host molecular soup also Podan. The previous class I will told you this Podan contains four donor site or four nitrogen atom donor site, and they'll make a complex with this metal atom like that. So in some complex they will forming a 5 member ring also. Here we can see 1, 2, 3, 4, 5, 6, and here also it is forming a 6 member ring like that.
Good evening, sir. Pardon, sir. Hello.
हाँ बोलिए.
Uh, Sir, will you be sharing these study materials?
Yes, yes. If one of
Uh,
one of your class member, they can contact me.
Sir,
Uh,
can we have your number?
Maybe my number is available in your group, WhatsApp group.
Uh,
Okay, on last of the class, or after few times, I will in the message box I wrote my
okay,
number.
okay, okay. Thank you so much.
Okay,
Thank you, sir.
okay. So one
Okay,
of
thank you.
your member of your class, they can collect it from me.
Okay, sir. Thank you, sir.
Okay. So you can see here also these two NH groups, this NH and NS, they are forming 6 member rings, but on the side you can see here, these are forming 5 member rings. So these types of gelatin covalents get more stability because they contain both 6 member rings along with the 4 member ring, 5 member rings also. Here also you can see this number of member rings just like 1, 2, 3, 4, 5. But here this is 1, 2, 3, 4, 5, 6. So this complex is forming along with the 5 member rings, along with the also the 6 member rings. Okay. So these types of complex, their stability is more because they contain both 5 member and 6 member rings. That doesn't mean if you make 7 member or 8 member or 9 member ring, the stability will be more. The stability gradually decreases with the increase in the flexibility inside the structure. So this is the representation of a 5 member ring. This is the representation of a 6 member cylinder ring. That means, particularly the organic compounds or simply the non-cyclic chains, and if they're forming a covalent bond, the general angle or optimal angle will be 109.5 degree. So when it will be forming a 5 member ring or 6 member ring, the angle value it is not exactly 109.5 degree, but it is in between 90 to 109.5 degree, which is a stable covalent bond. We can consider it just like a stable covalent bond. Okay. So if the further we increases the ring size, then this angle will deviate. The angle will gradually increases. If the angle will gradually increases, we can say the flexibility inside the ring will increases, and with increase in flexibility, the stability gradually decreases. So when a metal complex, a metal, it is coordinated with a host molecule, definitely they will form a stable complex. And this is the thermodynamic expression of this host guest interaction. That means AB. AB means this is a host guest. Consider one is host, another is guest, or AB. We can consider it just like a two different guests. When AB making a interaction with a host, and this change in Gibbs free energy due to A guest, and this is del Gp. This is the change in Gibbs free energy due to guest B, and del Gs. This is the additional Gibbs free energy which is created. Along with these individual effects, initially of this material I told you, this A and B we can consider just like the free energy site of arises due to A host, it is due to B host. For this del Gs, it will arises due to the combined effect of both A and B. So this extra del Gs value, it is providing the extra stability to the complex. That's why we can say this is the bigger contribution, is the important contribution due to this cooperative effect. Okay, so if this del Gs value, this change in Gibbs free energy value, it is negative, then the binding will be less favorable. So if this value will be positive, we can say the overall del G AB0, it will be bigger. If this del G S value, it will be negative, we can say the binding is less favorable. If this del G S value, it will be more than 0 or it is positive, we can say the binding tendency is enhanced. So we can say the chelation process or chelate complex formation, it is a type of positive cooperative effect between donor atom with the ligands. So we can summarize all the things, particularly what are the factors that affect the chelate effect. Particularly one of the factors is ligand structure. So ligand structure has the biggest role in formation of a chelate effect. So if you are taking a monodental ligand, they cannot never form a chelate complex. So you need to take a bidentate, tridentate, or polydental ligand. Particularly, we can say in one sentence, you need to take a polydental ligand to formation of a chelate complex. Second thing is that the ring size is also another factor. If you are forming a three member ring, and in some complex you are forming a five member ring, then definitely the five member complex stability will be more comparative to the three member ring. Then third factor is the solvent factor. So solvent particularly makes the biggest interaction with the metal and ligand. So after 3 to 4 slides, we will discuss about how solvent can impact the interaction in between the metal and ligand. So when the solvent separation occurs, that means initially when the host and guest molecule, it will interact with each other. Along with their interaction, they are attached with some solvent molecule. So when the host and guest molecule complex, it will form. Finally, there will be some separation of solvent molecule. So if the separation of solvent molecule from the host guest complex, it will be easier. Then there will be more number of free solvent molecules. If there will be more number of free solvent molecules, the entropy will be bigger. Okay, so solvent effect we'll discuss separately the last part or in the next class, but it is a bigger role in the metal ligand chelation process. Then another thing is the metal ion properties. So definitely metal should have a greater charge to interact with the ligand because the ligand has a electron density. So if the metal center has a positive charge environment, it will be more, it can more easily interact with the ligand. So definitely metal should have a greater positive charge density that can interact with the negative ligand. So next effect is that this is all are the cooperative effect. That means after the chelation, or we can say after the interaction of metal ligand, the cooperative tendency or metals, the complex stability, it will gradually increases. So next part we will discuss about the anti-cooperative effect. So initially I told you what's anti-cooperative. So when the binding of one guest molecule to the host site affect the binding affinity of another site. That means if initially one guest it will bind with the host molecule, then it makes an environment just like that. The another guest molecule, it cannot easily interact with the host. This is called anti-cooperative effect. That means binding of one guest molecule, it is not favoring the environment just like to interact for the another guest molecule. So it has a, there may be both positive as well as negative cooperative effect. So particularly the negative cooperative effect is called also as simply as anti-cooperative effect. So what is the positive cooperative effect and what is negative cooperative effect? We'll again distinguish in between them. So simple thing, binding of the first guest in the first guest increases the affinity for the second. This is called positive. And the examples are hemoglobin, particularly hemoglobin. In one hemoglobin, it can attach four oxygen molecules. So binding of one hemoglobin or one oxygen molecule with the hemoglobin complex, it favor the binding of another oxygen molecule. So one hemoglobin complex, it can form a tetrapod-like complex, or it can bind four oxygen molecules. So binding of first oxygen molecule favors the binding of second, and the second it will favors binding of third, just like that. So you can remember in your bioinorganic chemist the cooperative effect in hemoglobin, where K1 will be greater than K2, and it will be greater than K3, and it will be greater than K4, like that. You can remember from your BSc note or BSc material. That means the binding efficiency of the first one, it will be bigger. It will enhance the binding efficiency of the second one, then further like that. So this types of positive cooperative effect is, it is called homotropic effect. It is called homotropic effect. Then the negative cooperative effect, you can see here the binding of the first reduces the affinity of the subsequent gas. So these types of effect are found in rare, but in some metal enzyme complex you can find out these types of cooperative effects. So there are other types of effects also called allosteric effects. So binding at one site influences the another, often spatially or site. Okay, so these are also another types of effect. So if the binding of one side, it can affect the another side also. So it can affect it in a positive way also, in negative way also. So it depends upon particularly the guest host environment. Okay, so next we'll discuss about homotropic and heterotropic. So in homotropic, basically the guest molecules are identical, and heterotropic, the guest molecules are different. Just like in our blood, hemoglobin, it can attach to oxygen also, and it can also attach to carbon dioxide gas also. Okay, sigmoidal curve, it will form by the interaction of oxygen with hemoglobin or myoglobin. Okay, so there will again there will be a mathematical expression from which we can identify these thermodynamic stabilities. So here you can see there is a equation Km1 plus divided by Km and Mt minus M, like that. So here M is the number of occupied binding sites and T is the number of total sites. That means H is the host molecule. H provides T sites to occupy by the guest molecule. But guest molecule only interacts with the M sites. M sites means बुझियो M active sites that were occupied by the guest molecules. And T is the maximum number of active sites that are available by the host molecule. Yes or no? And if you take these types of expression, you can find out this mathematical expression, and if this ratio value it is more than the theoretical value, then it is called a positive cooperative effect. If the ratio is more than 1, or ratio will be more positive, then we can say this is a positive cooperative effect. If the ratio is equal to theoretical prediction, then we can say this will be non-cooperative effect. If the ratio value is a negative value or less than the theoretical assumption value, then it will be told as just like as a cooperative, anti-cooperative effect or a negative cooperative effect. So from this mathematical expression, we can calculate whether this guest host interaction it is positive cooperative effect, or whether it is a negative, or whether it is anti-cooperative effect. You just need to calculate these values. M means number of active sites provided by the host. Sorry, M means the number of occupied sites provided by the binding sites by the guest molecule, and T is the total number of active sites provided by the host molecules. That means in this expression, T value it will be always more than M value, or it can be equal to M value. And here the M value it cannot be more than T. It can be less than T, or it can be equal to the T. So the next important factor is that selectivity. So when there will be guest host interaction occurs, then definitely selectivity will be an important parameter. Okay, so along with selectivity, the other factors are also important. Cooperative among the binding groups, already we are discussing here. Reorganization and the rigidity of host to reduce the entropic cost of binding. That means after binding, whether the overall complex's rigidity or overall complex's entropy value it will gradually increases or decreases, and the structure of host and guest and their binding site, they must have structurally complementary. That means if a host provides a active site, a proper active site, then proper provides a proper cavity site, then the molecule with the appropriate size they can fit into it, and they must be chemically complementary. Means if this active site provides a positive atmosphere, positive charge species, then the host molecules or guest molecules active site it should be just it providing it should be just like it providing a negative charge sphere. Okay, so when the charge sphere or interacting sites are complementary, they can more strongly bind with each other. So here you can see in hydrogen bonding, just like amines are donors and carboxylates are acceptors. That means from one of the host and guest, out of them, anyone, if one is providing amine donors and another is providing carboxylate end groups, then this amine and carboxylate they can interact with each other. And these types of interaction we can say they can form hydrogen bonding. Amine groups means just like in amino acids, we can see one of the end it is containing an S3 plus group, and another it is linked to the another group which is providing COO minus group, carboxylate group. So this type of interaction is also called hydrogen bonding. Okay, that means out of one of them, any host and guest, if you one end is providing NH3 plus and another end is providing carboxylate group, then definitely the positive charge they can easily interact with the negative charge, and these two we can say both are complementary to each other. Second thing is that just like lock key principle, we can previously discussed. Lock is the enzyme and it is providing a cavity size or cavity, and key is the substrate. They can fit into it and they will form a enzyme substrate complex. So if the cavity size it will be proper according to guest, then we can say the lock and key or enzyme and substrate both are complementary to each other. So in next we can discuss about the induced fit model. So when the guest binds the host undergoes conformational change. That means after the binding with host molecule along with guest, they can make some conformational change in between them. So for a better fit or for different properties takes place. Sometimes initially the proper active site or proper cavity size is available, and in some model also, and some enzyme and substrate complex also, after the interaction, they make some other conformational changes to form a stable complex also. And this can be explained. These types of induced feed model. This is called induced feed model. These types of induced feed model, they can be explained by some trigger processes or that are happening particularly in our muscle contraction also. So in figure 7, we can see this is a flexible enzyme site. This is a substrate. It's coming on this side. It's interacting with it just like that, and it's making, you can see this is enzyme and substrate, and the active site is like that, and this is coming and they can fit into it. After fitting they will make some conformational changes and they will form a complex like that. This is called induced fit model. Initially the cavity size is not much more, just like guessed, just like the substrate. For after the connection of substrate with this host molecule, they change its cavity size to form a stable complex, and finally the complex will be like that. So the upper one is log key model. That means before the interaction with the substrate, the enzyme exactly provide the proper cavity size for the substrate to interact with it, just like that. This is the exact cavity size, the substrate will fit into it. But in induced fit model, after the interaction of the substrate with the enzyme, they make some conformational change. Here they'll increase the cavity size after the interaction, and then the substrate they can fit into it. This is called induced fit. That means the substrate makes some cavity size change in the host molecule. Okay, that's why this is called induced fit model. Then another important parameter is the complementary. So the definition of complementary, particularly, it is matching with the size, shape, and chemical functionalities between the host and guest molecule. That means that the host and guest size should be proper, and it should be proper in shape. And chemical functionality means, before I told you, the interaction. Chemical functionality means, always remember the interaction. One should be positive charge, another should be negative charge. One should be behave like a donor, another should be behave like a acceptor. Then there should be, we can told it just like guest holder, guest and host are both are complementary to each other. So sometimes this is called structural complementary, and sometimes the complementary behavior, it will be just like chemical complementary, just like acid-base interaction, hydrogen bonding. And sometimes it may be just like hydrophobic effects. So another acid-base interaction means one of the side it may just behave like acid, or another side it may behave just like a base also. So when, just like in Lewis acid and Lewis base, so Lewis acid they can accept electrons, and Lewis base they can just provide electrons, electron pairs. So if one end it will behave like acids, then another end it can be behave like base. If the guest and host they contain the end molecules or terminal molecules, just like host contains the acid molecules, guest contain the base molecules, basic molecules, then they can make an interaction. So this interaction it will be known as acid-base interaction. In BSc, you already studied it. HSAB interaction, hard soft acid-base principle. So basically, the hard species are smaller in size, which are non-polarizable, just like H plus, Na plus, O minus, and soft acids are just like polarizable, and it is bigger in size. Sulfur atoms, donor atoms, nitrogen donor atoms, platinum 2 plus atoms. So the rule is hard, hard, and soft, soft interaction. That means hard acid refers to bound with the hard bases, and soft acid refers to bound with the soft bases. So in particularly in brown ether, the oxygen atoms or oxygen donor atoms stabilizes the metal cations. So specifically, oxygens are the hard bases. You just remember in brown ether examples. So these types of oxygen in brown ether complex, they particularly make, or they particularly trap the cations, just like lithium, sodium, or cesium, which are the hard cations, or which are called just like as a hard acids. And here the oxygen donor atoms that will stabilizes that type of cations are the hard bases. These are called as hard bases. Similarly, we can see here in AJA macrocycles or other types of macrocycles, this is one of the macrocyclic ligands that provide nitrogen donor atoms. Just like crown ether provide oxygen donor atoms, they provide nitrogen donor atoms. So this nitrogen donor atoms, this is a soft side, or this will behave just like a soft base. So it can bind the transition metal atoms more strongly, because the transition metals atoms are generally soft in nature. So according to HSAV principle, so hard interaction it will be more preferable or stable, and soft interaction it will be more preferable. So that's why gram ether complexes they can trap only the hard metal ions, just like lithium, sodium, potassium, cesium, like that. So you can read out here also what is cooperativity, like is mentioned on the side also. Okay. Already we have discussed. So the next important parameter is that kinetic controlled and thermodynamically controlled binding processes. So for a functional host-guest system, the most discriminate between competing guest and bind preferentially to target the species. So this, for targeting the species, there will be two types. The targeting it can be done by two types: thermodynamically and kinetically. So thermodynamic stability is, it is defined as the preference of a host for a guest over another in terms of binding strength. If the binding strength in between metal and the ligand, or in between guest and host, it will be strong. If the bond it will be strong, then we can say it is thermodynamically stable, and the complex is thermodynamically selectivity. Okay. So the thermodynamic selectivity or thermodynamic stability, it can be determined by the equilibrium constant values. By the equilibrium constant values, here you can see here, this K and Kb, these both are equilibrium binding constants. So Ka is the equilibrium binding constants of host with the guest A, and Kb is the equilibrium binding constant of guest B with the host molecules. So from by comparing the equilibrium constant binding constant values, we can say this guest binding forming more stable complex with this host, or this guest forming more stable complex with this host. So the thermodynamical stability, it is predicted from the equilibrium constant values. So this equilibrium constant relation, see, we can also explain in another way, just like that, del G equal to minus RT ln K. So here this K is the equilibrium constant and del G is the Gibbs free energy. So particularly when we are discussing about thermodynamic value, so the determining factor are particularly the del G value or K value or equilibrium constant value. That means Gibbs free energy value or equilibrium constant value. If K value will be more positive, then this negative part will be also more negative. If this part will be more negative, then the del G value will be more negative. If the del G will be more negative, the reaction will be more physical. So for good thermodynamic stability, we need a high positive equilibrium constant value, or we need a more negative del G value. Okay, so here R is the gas constant, and it is the temperature of this relation. So the energy of association, it can be controlled to some extent when the host system is designed by applying the design principles such as Gillette and microcyclic effects. Okay, so the both the parameters Gillette and microcyclic, they can also contribute some stability to the complex also. So another factor is kinetic selectivity. So kinetic selectivity basically based on a very different principle to thermodynamic selectivity. It is a preference of host for one guest over another based on the reaction state, not equilibrium stability. So particularly if you can say one host is available along with two guest molecule. So the guest molecule, out of the two guest molecule, which guest molecule first interact with the host molecule, it will it will form a kinetic stable complex. We can say this guest host interaction is kinetically stable. The bond strength in between the guest host, it may be weaker, but if it is forming in a faster rate or it is forming initially, then we can say this is kinetically selective complex. So it is not determined by equilibrium stability. It is determined by the activation energy. Yes or no? So for thermodynamic selectivity, the basic parameter is the equilibrium constant and it gives free energy. But for kinetic selectivity, the basic parameter is that the activation energy. From activation energy value, we can calculate which one's kinetic stability will be better, which one's kinetic stability will be less. So this principle involved in a host may be convert one substrate faster even if it binds less strongly. So the metal ligand interaction and the host guest interaction, it may be less strength. The strength wise it is maybe less, but if the complex is forming in a small time interval or in a faster way, then I can say this is a kinetic stable complex. So the kinetic stability depends upon the rate of transformation, not equilibrium binding strength. So we can say the kinetic stable complex has a high activation energy barrier. So if the activation energy barrier will be high, we can say the kinetic stable complex it will be good kinetic stable complex. However, another possible complex may be lower free energy or permanent stability, but be slow to form due to high activation energy. So thermodynamic stable product, it is forming in a slower rate, or it can take longer time to form, but its strength is equilibrium strength is much more high. But kinetic stable product, it is take less time to form. So in ligand exchange reaction, generally a bulky ligand may bind quickly. So the interaction of generally a bulk ligand with the metal, or the interaction of a bulky host with the guest, this is called a kinetic interaction. But over a time, smaller ligands can form a more stable complex. This is called thermodynamic product. So particularly thermodynamic stable complexes, it can take larger time, but it is comparatively more stable. But the product which form in a faster rate or in a slower time, we can say this is kinetically stable. So temperature basically plays a key role to determine whether the complex is thermodynamic stable or whether the complex is kinetic stable. So for kinetic control, the product formation the fastest due to lower activation energy barrier. So in kinetic stable complex, the activation energy barrier is very, very low, or it may be less stable, but it dominates at lower temperature. And generally, the thermodynamic stable products, it dominates at the higher temperature. Okay, and it is the most stable. Thermodynamic one will be the most stable, but it can take consume more time, or it can pass through a high activation energy barrier, or it generally dominates at higher temperature. So a crown ether may fast bind a smaller alkali metal ions. It is we can say it is kinetically favored, but at higher temperature it arranges to bind a larger ion fits better or thermodynamically favored. So the we can consider just like a interaction of a smaller metal ion with crown ether complex. It is a kinetic stable complex, but if you supply a larger ion, also it can interact with the crown ether complex. But the condition should be like that. It should be at higher temperature. So at high temperature, the interaction of crown ether with a bigger metal ion, which is thermodynamically favored. So this is all about thermodynamic and kinetic stability of the metal complexes. So these are not much more complicated things. In BSc, you already studied it, the metal solution complex, the entropy factors. Okay, so they can ask question also. What is a give me a brief discussion about the cooperative effect. Give me a big brief discussion about the anti-cooperative effect. But after them, cooperative effect is much more selective. They can ask the long question also. What is cooperative effect? Mention all the thermodynamic parameters that affects the cooperative effect. You can mention the Gibbs free energy, entropy factor, chelation process, all these things. So in next class, we will discuss about solvent effects and some other important topics of supramolecular chemistry. So if you have any question, you can ask.
Hello.
Hello?
Sir, screen is not coming.
No, oh no, already course is over. If you've done any doubt from the material, you can ask. Now it is visible.
Yes, sir.
So you can note it my
Hello,
number.
sir.
Hello.
Yes, sir.
Uh,
Yes,
you
sir.
can
Yes,
note
sir.
my number. If you have any need any material regarding this class, you can message me. I'll send one of you,
Okay,
and
sir.
you will circulate
Okay.
among all of them. Seven eight
Yes, sir.
five four
Sure.
eight
78548
433
433
61.
61. Sir, this one. No?
Yes, yes, right.
Okay. Thank you, sir. Sir, may I
Thank
ask
you.
one small question that is just coming in
Yes,
my
yes.
mind? There's
You can ask.
like uh, can we synthesize easily these supramolecules in the laboratory?
Already you can synthesize these molecules. There are so many works on supramolecular chemists. In our central institutes, IIT, Niger, they are also working on supramolecular chemistry also. So for
Okay.
supramolecular chemist, these types of complex formation, one of the basic thing is the
Mm-hmm.
post synthesis. So the difficult step is that the final step is the when you will form this cycle. You can form a linear cell
Mm-hmm.
like that initially. You can form a linear cell like that, and finally you will cyclize the linear chain to form a complex. And this step is the actually the difficult step. So when
Okay.
I'm working in my research, particularly, we are taking the
Your topic
hemoglobin
is
type.
supramolecular, sir.
No, exactly not supramolecular. My topic is actually porphyrin-based complexes or the bioinorganic
Pardon, sir?
complexes,
Acha, acha.
porphyrin-based complexes. In
Porphyrin.
hemoglobin structure, uh,
Yeah,
the
yeah, yeah. That
four
five
pyral
ring.
rings are present.
Yes,
Okay,
iron means around
four
magnesium,
rings,
iron.
uh,
Around iron.
iron, just like these types of
Mm.
rings. So initially, we can take any ring along with any functional group complexes, just like aldehyde or other functional groups. So in first step, you will combine or couple
Mm-hmm.
two ring complexes to make a linear chain. Similarly,
Okay.
you can also make another types of complex, another two ring. They can couple to
Mm.
form a coupling reaction. So whatever it may be,
Okay.
you can form easily the linear complex. But when the final step is the cyclization. Okay, so when you will cyclize it, finally, you are using a strong acid. Okay, so this is just type
Okay.
a selective process. You are
Mm-hmm.
applying many types of strong acid. In any acid, it can fit and it can cyclized. So when there will be cyclization occurs, we can get a perfect crystal, You can analysis it by XRT analysis. You can confirm it. There is the cyclation process is completed. So after the formation of the cyclic complex, you need to
So
supply so many
XRD means
met
we'll be getting the compound in solid state, right?
huh,
Or
we can getting we are getting the compound in solid state. We need to get the compound in solid state for XRT. Okay. We need to
okay.
form
So
in the form of
basically, right
crystal.
now, where you are teaching in IGNOU
I
itself?
am teaching no, I am teaching in degree college level, plus three
Where?
students, degree college level, just like plus three students.
No, no, where?
Kendrapada Autonomous College.
Oh, you are in Kendrapara itself.
Yes.
Okay, okay, okay. Okay, so sir,
Okay.
regarding that, okay, sir, fine, sir. Thank you.
Okay, so metallation final जो host ghost interaction. This is also a selective process. You can supply many metals, but you can supply the preferable metals. You can choose selective copper, palladium, platinum, just like that. And finally, if the
Mhm.
metallation, the metal will fit, and finally you can stop the process and confirm that these types of basically these types of supramolecular complexes are useful in our biological systems, particularly if
Okay.
in our body a toxic type elements suppose more of copper, more of calcium,
Hmm.
also it can be hazardous for our biological health systems. So if
It's
you want to
toxicologist
eliminate
circle.
toxicology, particularly if you want to
Hmm.
eliminate some
Hmm.
preferable metals, you can
Hmm.
supply some preferable macrocyclic links that can trap with the metals, and that can also
It will bind and
soluble in
flush
the
out.
plus out. But the here
Okay.
is also another step. The solubility should be good, and the binding
Okay.
tendency with this macrocyclic ligand with this toxic metal it should be high. If the binding tendency
Okay.
it will be more, it can
Mm-hmm.
preferably choose the specific types of metals. So then again you
Okay.
can remove through the biological process.
Okay. Thank you so much, sir. Teaching was
Thank you.
also very nice. Thank you so much, sir.
Okay.